State what is meant by an ideal gas. Ideal gas is a gas that obeys the equation pressure times the volume divided by temperature equals to constant, or P times V equals to nRT. Storage cylinder for an ideal gas has a volume of 3 times 10 to minus 4 cubic meter. The gas is at a temperature of 23 degrees Celsius and a pressure of 5 times 10 to 7 Pascal. Shows that amount of gas in a cylinder is 6.1 mole. It is ideal gas, so we're going to use ideal gas equation PV equals to nRT. The first thing we need to do is we need to convert 23 degrees Celsius into Kelvin, because capital T here is in Kelvin. That is 273 plus 23, which is 296 Kelvin. The pressure is 5 times 10 to 7 times the volume 3 times 10 to minus 4, N times universal gas constant 8.31 times temperature in Kelvin 296, and N equals to 5 times 10 to 7 times 3 times 10 to minus 4 divided by 8.31 times 296. That gives us 6.1 mole. The gas leaks slowly from a cylinder so that after a time of 35 days, the pressure has reduced by 0.4%. The temperature remains constant. State the average rate in atoms per second at which gas atoms escaped from the cylinder. So we need to find the rate of escaped atoms. As we know, PV equals to nRT, and the temperature remains constant, so T is constant. And we know this is the fixed volume, so volume is constant. So P our N equals to RT our V. R is constant, temperature is constant, fixed volume, so P our N is constant. That means P pressure is proportional to amount of substance. So the pressure is proportional to amount of substance, or mole number. Since the pressure is proportional to amount of substance, or mole number, the pressure has reduced by 0.40%. As the pressure is proportional to amount of substance, the amount of substance reduced by 0.40% as well. So the N lost equals to 0.40% times 6.1 mole, which is 0.004 times 6.1. That gives us 0.0244 mole. As we know, mole number equals to total number of particles divided by Avogadro constant, and the total number of particles equals to mole number times Avogadro constant. Now we can find the lost particles. N equals to 0.0244 times Avogadro constant 6.02 times 10 to 23 atoms. Number of molecules escaped are 1.47 times 10 to 22 atoms. The question asking the average rate at which gas atoms escaped from the cylinder. So the rate equals to total number of gas escaped divided by time taken. 1.47 times 10 to 22, 35 days equals to 35 times 1 day is 24 hour, 1 hour is 60 minutes, 1 minute is 60 seconds. That gives us 4.9 times 10 to 15 per second. This means, in average, 4.9 times 10 to 15 molecules escaped in every second. A fixed mass of gas has an initial volume of 5 times 10 to minus 4 cubic meter at a pressure of 2.40 times 10 to 5 Pascal and a temperature of 288 Kelvin. It is heated at a constant pressure so that in its final state, the volume is 14.5 times 10 to minus 4 cubic meter at a temperature of 835 Kelvin, as illustrated in the figure. Shows that these two states provide evidence that the gas behaves as an ideal gas. We just discussed definition of ideal gas. Ideal gas is a gas that obeys PV over T equals to constant, or pressure times volume divided by temperature equals to constant. So initially we have PV over T. Pressure, initial pressure 2.40 times 10 to 5 times volume is 5 times 10 to minus 4, and initial temperature is 288. And this gives us 0.417. And finally, PV over T equals to 2.40 times 10 to 5 times 14.5 times 10 to minus 4 divided by final temperature 835 Kelvin. That also gives us 0.417. This indicates that it is ideal gas, as PV over T equals to constant, which is 0.417. B, the total thermal energy supplied to the gas for this change is 569 joule. Determine the external work done. We know for thermal physics, if the pressure is constant, we look at pressure is constant here. Pressure is 2.40 times 10 to 5. For constant pressure, we have work done equals to pressure times delta V. And constant pressure here is 2.40 times 10 to 5. And the change in volume is final volume 14.5 minus initial volume 5 times 10 to minus 4. That gives us 228 joule. Explain what is meant by Avogadro constant. It is number of atoms in 12 gram of carbon 12. B, argon 40 may be assumed to be an ideal gas. A mass of 3.2 gram of argon 40 has a volume of 210 cubic centimeter at a temperature of 37 degrees Celsius. Determine for this mass of argon 40 gas the amount in mole. The question asking the amount in mole, which is mole number, that is mass divided by molar mass. N is mole number, M, small m is mass, capital M is molar mass. So the mass is 3.2 and molar mass is 40. That gives us 0.08 mole. Determine for this mass of argon 40 gas the pressure. It is ideal gas, so we have a PV equals to nRT. So we need to convert non-SI unit into SI unit here. The volume is 210 cubic centimeters. That is 210 times 10 to minus 6 cubic meter. And the temperature is 37 degrees Celsius. We convert that into Kelvin, which is 273 plus 37, that is 310 Kelvin. Now we can plug in 210 times 10 to minus 6 equals to mole number 0.08 times 8.31 times 310. That gives us and finally 9.8 times 10 to 5 Pascal. A constant mass of an ideal gas has a volume of 3.49 times 10 to 3 cubic centimeter at a temperature of 21 degrees Celsius. when a gas is heated, 565 joule of thermal energy cause it to expand to a volume of 3.87 times 10 to 3 cubic centimeter at 53 degrees Celsius. This is illustrated in figure. Shows that the initial and final pressure of the gas are equal. For ideal gas, we know PV, our T, is constant. And we need to convert cubic centimeter into cubic meter. That is 3.49 times 10 to 3 times 10 to minus 6 cubic meter. Similarly, 3.87 times 10 to 3 times 10 to minus 6 cubic meter. And the temperature, 273 plus 21, that is 294 Kelvin. And temperature in Kelvin, 273 plus 53, we get 326 Kelvin. As the pressure is constant, initially we have V over T, and the volume is 3.49 times 10 to 3 times 10 to minus 6 divided by 294. Temperature must be in Kelvin. That gives us 1.19 times 10 to minus 5. Finally, we do the same. V over T equals to 387 times 10 to 3 times 10 to minus 6 divided by 326 Kelvin. That also gives us 1.19 times 10 to minus 5. So both values of V over T is constant. So pressure is constant. The B, the pressure of the gas is 4.20 times 10 to 5 Pascal. For this heating of a gas, calculate the work done by the gas. For constant pressure, work done is equals to pressure times change in volume. However, we need to convert cubic centimeter into cubic meter. 3.49 times 10 to 3 times 10 to minus 6 cubic meter. Similarly, 3.87 times 10 to 3 times 10 to minus 6 cubic meter. Now we can find work done, which is equals to constant pressure times change in volume. Pressure 4.2 times 10 to 5 times final volume 3.87 minus initial volume 3.49 times 10 to 3 times 10 to minus 6. That gives us 160 joule. State what is meant by an ideal gas. 3-mark question. First, we already know the gas at OB equation, PV over T equals to constant, or PV equals to N over T. P is pressure, V is volume, T is temperature in Kelvin. And finally, for all values of P, V, and T, N is constant, or it's a fixed mass gas. B, two cylinders A and B are connected by a tube of negligible volume, as shown in figure 2.1. Initially, tap T is closed. The cylinders contain an ideal gas at a different pressure. So initially, the tap is closed and it contains ideal gases. I, cylinder A, has a constant volume of 2.5 times 10 to 3 cubic centimeter and contains gas at pressure 3.4 times 10 to 5 Pascal and a temperature 300 Kelvin. Shows that cylinder A contains 0.34 mole of gas. We need to convert a cubic centimeter into cubic meter. So that is 2.5 times 10 to 3 times 10 to minus 6 cubic meter. And as it is ideal gas, we have PV equals to N over T. Pressure is 3.4 times 10 to 5 times 2.5 times 10 to 3 times 10 to minus 6 in cubic meter equals N times universal gas constant is 8.31 times T 300. Solve this, we get N equals to 0.34 mole. So cylinder A contains 0.34 mole of gas. Cylinder B has a constant volume of 1.6 times 10 to 3 cubic centimeter and contains 0.2 mole of gas. When tap T is opened, the pressure of the gas in both cylinder is 3.9 times 10 to 5 Pascal, which means both cylinder has the same pressure, 3.9 times 10 to 5 Pascal. No thermal energy enters or leaves the gas. Determine the final temperature of the gas. The total volume is the volume in cylinder A plus the volume in cylinder B. And the amount of substance equals to mole number in A plus the mole number in B. They have the common temperature, or they reach thermal equilibrium, so the final temperature should be same T, and that's what we are looking for. And when the tap open, both cylinder has the same pressure, 3.9 times 10 to 5 Pascal. So we have a V1 and we have a V2. We convert them into cubic meter. 2.5 times 10 to 3 times 10 to minus 6 cubic meter. 1.6 times 10 to 3 times 10 to minus 6 cubic meter. N1 equals to 0.34 mole. We found in previous slide. N2 is given 0.20 mole. Now, for the total amount of gas, we have pressure is same, volume is added, amount of substance N1 and N2 is added. So we have P V1 plus V2 equals to N1 plus N2 times RT. Pressure is 3.9 times 10 to 5 times 2.5 plus 1.6 times 10 to 3 times 10 to minus 6. That's the total volume. And amount of substance 0.34 plus 0.20 times 8.31 times T. And the final temperature equals to 360 Kelvin. The volume of an ideal gas in a cylinder is 1.8 times 10 to minus 3 cubic meter at a pressure of 2.6 times 10 to 5 Pascal and a temperature of 297 Kelvin as illustrated in figure. The thermal energy required to raise the temperature by 1 Kelvin of 1 mole of gas at constant volume is 12.5 joule. The gas is heated at a constant volume such that the internal energy of the gas increased by 95 joule. Calculate the amount of gas in mole in the cylinder. As it is a ideal gas, we have PV equals to nRT. So the volume is 1.8 times 10 to minus 3 and the pressure is 2.6 times 10 to 5 equals to N times 8.31 times the temperature in Kelvin, 297. That gives us 0.19 mole. The amount of gas in mole in the cylinder is 0.19 mole. Calculate the rise in temperature of the gas. Let's take a look at this line. Thermal energy required to raise the temperature by 1 Kelvin over 1 mole of gas at a constant volume is 12.5 joule. That is the definition of a specific heat capacity. Specific heat capacity is thermal energy needed to raise the temperature by 1 Kelvin over 1 mole or 1 kilogram of substance. So that is 12.5 joule per mole per Kelvin. And we know the internal energy of the gas increased by 95 joule. That means delta Q equals to MC delta T. The delta Q is the internal energy of the gas increased, which is 95 equals to 0.19 mole times 12.5 joule per mole per Kelvin times change in temperature in Kelvin. So moles are cancel out and we get change in temperature is 40 Kelvin.